Hi everyone, so we're going to see D.9, which is on drug detection and analysis. So for this chapter, you should be able to use IR, mass spectroscopy, and HNMR to interpret organic structure. So we're going to see one of the structures, so C3H6O2. So we're given these three spectra. So let's look at the IR. So it is C3H6O2. So from the formula itself, we can see that there's O2 here. So probably it's an ester. So we would be looking at this or this. And when you look at the IR here, you see a broad peak. So this is a broad peak and it occurs at wave number a little bit less than 3000. So most probably this is the OH stretching in COOH. So this is typical of this type of stretching, and if you want to confirm in the data booklet, you will see the OH OH here in carboxylic acid. So it is a little bit less than 3000 centimeter minus 1. So strong, very broad. And then we have this peak here, which is B. So this is at around 1700 centimeter minus 1. And this is the C double bond O stretching here. So you can see this. So this is in carboxylic acid. So it confirms that it is COOH. And here you have a stretching at around 1200 centimeter minus 1, and if we check here around 1200 you have the CO. So this is the CO, this is the C double bond O, so it confirms that it contains C double bond O OH. If we look at the mass spectrum, we're going to see the strong peak at 74. So this is probably the molecular ion peak, so C3H6O2 plus. Because we are doubting that there is C double bond OH, so if we look here, M over Z value 45, so this is for COOH plus, and if you check in the data booklet you will find it here. So 45 is COOH. And if you do 74 minus 45, so 29, so you have a peak here, 29, a strong peak. M over Z is 29, so this corresponds to CH3, CH2. So we know that there is COOH, we know that there is CH3, CH2. Alright, so from these two spectra. Let's look at the NMR now. NMR, you have one proton here at range, so chemical shift around 12. So the high values of chemical shift, so around 12, you only have OH in carboxylic acid. So you know it's the H in COOH. So no neighbor, so this is a singlet. And because of the electronegativity and the influence of the COO, so the chemical shift value is very high. And then you have 3 and 2. So 3 means that there's 3 hydrogens, so probably CH3. And 2 means there's 2 hydrogens, so probably CH2. And because they are next to each other, generally we know that it's CH3, CH2. And if you look at the CH3 peak here, you see that it is 1, 2, 3. So it is a triplet, which shows that it has 2 neighboring protons. And if we look at this one, you can see that there is 1, 2, 3, 4. So this is a quartet. And because it is a quartet, it shows that it has 3 neighboring protons. So this confirms that you have the CH3. So this gives an integration of 3. And it has 2 neighboring protons. So the 2 neighboring protons make it produce a triplet. And then you have the CH2 here, CH2. So it gives an integration of 2. And because it has 3 neighboring protons, it produces a quartet. And then you have the COOH, the H in the COOH that produces a singlet. So this one has no neighbors. So this is the final structure that has been deduced from the 3 spectra. So let's see this question, which is about meth, which is the substance of abuse, which is a stimulant. And when meth is manufactured, when it's made in labs, it usually includes impurities, and some of the impurities, some possible impurities are given here. But you're also given the IR spectrum, and from the IR spectrum you are supposed to deduce which impurity is present. Now the first thing that can be seen from the IR is you have a strong peak here. So at 3000 centimeter minus 1, and this is a strong peak, and you can see that it is also a broad peak here. But you can also see 2 peaks, right? Now when you see these 2 peaks here, this is very characteristic of NH peak. You see 2 bands at greater than 3000. So these are the 2 peaks that we see. So this is because of NH. So NH stretching produces these peaks. And also here, that strong peak, broad peak, this is because of the OH, right? So this is OH stretching. And we don't see anything particular about any C double bond O peak. There is nothing here. So normally C double bond O around 1700. There is no strong peak here. So there is no C double bond O. It's not present. And if we look at, so this is the only thing that we're looking for in the molecule. So this is C double bond O. This is not present. So it's not this one. And because you have an OH here and you have NH, so OH stretching here, NH is here, and you can confirm that it's ephedrine as the impurity. Now let's see the second question. So you are asked how IR can be used to distinguish between morphine and heroin. So let's look at section 37 of the data booklet. You have the structure of morphine and heroin. Yeah. So if we look at the structures for IR, you have the peaks, wave numbers in section 26. So we're going to see what are the different peaks that you're going to get. So here you have OH. So over here you will have OH stretching. And if you look at heroin, there is no OH, but there is C double bond O and there is CO. So here you will see C double bond O and you will see CO. And that is it. Here, CO also here. And then you have CO also here. And these are the only characteristic peaks. The other ones are going to be minor and it would be very difficult to identify. The CN, there is nothing in the section 26 about CN bond stretching. So these are the only 2 that we will see in heroin. And in morphine, here is attached to the benzene ring. So you would see the OH in phenols. So here in alcohols and phenols, so it would be this peak. The IR of heroin will contain a strong peak at 1750 centimeter minus 1 due to the C double bond O stretching, and 1 peak due to CO stretching, which is in this range. So this is the difference. Now let's see the difference between aspirin and ibuprofen. So if you look at both of them, they have COOH. So that will not be a difference. But here you can see that aspirin, you have ester here. You have an ester linkage here. Right? So this is the CO in an ester. But here, this is a carboxylic acid. So carboxylic acid, but here you have an ester. And if you look at the peaks, so the CO will be the same, C double bond O will be the same in both of them. But here, in aspirin, you will have the CO stretching, which is present in esters. So you will have this peak over here. So put simply, the IR spectrum of aspirin will contain a strong peak at this range. I took this range from the data booklet over here, and this is due to CO stretching in the ester linkage that is present here. This peak is absent in the IR of ibuprofen.